In this paper, we present a new method for data-efficient visual-tactile model estimation called structured Bayesian meta-learning. We are inspired by how humans see and touch diverse objects in daily life, and we learn to associate how objects appear with how they feel. Given a new object, we use our experience of touching similar-looking object to predict how it feels. But if the object feels different from what we initially expected, we can quickly adapt our mental model to match the new experience. Existing work either assume homogeneous material, have no model adaptation, or directly train from simulate full observable visual tactile data. Our work is able to learn heterogeneous objects, have online adaptation, and learn from real-world partially observable data. First, we collect the dataset containing camera and force data, where the robot touches a diverse set of objects in real world. Here, we show a robot touching an artificial plant and how the corresponding joint torque reading changes on the right. Using this experience and experience from other similar plants, our method builds a prior distribution or visual-tactile models. The key technical contribution of the structured Bayesian meta-learning is that it enables learning priors from diverse objects. These objects have different sizes and geometries, so this standard meta-learning method that require a fixed dimensional input and output do not apply. Training objects differ in the dimensionality of their feature spaces, material spaces, and state spaces. Our structured approach uses a structure generation module to generate object-specific structures. These structures allow mapping from fixed dimensional material prior space to the input and output parameters, which have variable dimensionality. In this way, the structured prior can predict how plants parts that appear in a certain way feel on average. Given a novel object, the robot uses the prior to predict stiffness from the appearance alone. Here, the branch region is predicted to be stiffer than the leaf region, which corresponds to our intuition. Once the robot starts touching the plant, it updates the estimated stiffness map. For example, we can see the robot predict the leaf region to have very low stiffness at the beginning. But because there are branches behind the leaf, it produces a torque response that is higher than expectation. Then the robot will increase its estimated stiffness map to match the actual observation. Compared to an uninformed model shown on the left, our model produced much more plausible estimation given a much small number of touches. Overall, we present a method that enables meta-learning visual-tactile models prior from a diverse real-world object. In the future, we are interested to apply our method to other visual-tactile models, for example, finite element method or graph-based dynamics.